construction multiplied the pressure. Factories, warehouses, worker housing, bridges, and temporary industrial structures all relied heavily on lumber. Urban growth transformed forests into building materials with remarkable speed. Entire landscapes were effectively converted into the physical framework of industrial civilization. The numbers became alarming. Forestry officials, industrial planners, and government administrators increasingly recognized a dangerous imbalance between consumption and regeneration. Trees required decades to mature. Industry consumed them immediately. Nature operated on one timetable. Industry operated on another. The gap widened every year. German foresters had long maintained some of Europe's most advanced systems of woodland management. Scientific forestry, pioneered in German-speaking territories during the 18th and 19th centuries, sought to regulate harvesting and ensure long-term sustainability. Forests were measured, catalogued, and managed with extraordinary precision. But industrial expansion threatened even these carefully designed systems. Demand repeatedly exceeded expectations. Economic growth generated new requirements faster than planners could calculate them. Forecasts became obsolete. Consumption targets increased. Pressure mounted on every available resource. The challenge was not merely economic. It was strategic. Military planners understood that industrial strength determined national power. Railways enabled mobilization. Steel production supported armament industries. Mining fueled manufacturing. Any interruption in resource flows could weaken the empire's position within an increasingly competitive Europe. Resource extraction, therefore, became a matter of national importance. Engineers were asked to solve problems that once belonged to nature. How could forests be harvested faster? How could labor requirements be reduced? How could timber reach industrial centers more efficiently? How could production be expanded without slowing economic growth? The answers increasingly pointed toward mechanization. Steam power had already transformed transportation and manufacturing. Industrial machinery had revolutionized production inside factories. Many engineers believed similar principles could be applied to forestry itself. If machines could shape steel, weave textiles, and move freight, why could they not transform logging? The idea seemed logical. The consequences were less obvious. Because forests were not factories. Trees did not exist in orderly rows of interchangeable components. Landscapes contained irregular terrain, weather, biological complexity, and ecological relationships that machinery could not easily understand. Yet industrial thinking encouraged simplification. Complexity became an obstacle. Obstacles demanded solutions. The forest was recast as a production problem. German engineers began designing systems capable of overcoming the limitations of human labor. Larger saw mechanisms appeared. Steam-powered hauling equipment expanded. Specialized rail systems penetrated deeper into woodland regions. Mechanical extraction methods evolved year after year. What had once required dozens of men could increasingly be accomplished by a handful of operators directing immense machines. Productivity soared. So did expectations. The industrial crisis was never simply a shortage of resources. It was a collision between two forces moving at radically different speeds, the slow growth of nature and the accelerating appetite of industry. German engineers stood between them. And their machines would become the bridge. Long before steel giants entered the woods, the forest moved according to a different rhythm. The work began with daylight. At first light, teams of lumbermen entered the trees carrying axes, crosscut saws, wedges, ropes, and little else. The sounds of industry were absent. There were no engines, no hydraulic systems, no clouds of exhaust. Only the steady impact of steel against wood and the echo that followed through the canopy. Progress was measured in effort. A single large tree could demand hours of labor. Men studied its lean, examined surrounding growth, and planned the direction of its fall. Every cut required judgment. Every strike consumed energy. Success depended not on horsepower but on experience accumulated over years of work. The forest imposed discipline. Weather determined schedules. Rain transformed trails into mud. Snow restricted movement. Wind altered felling conditions. Terrain dictated what could be harvested and what would remain untouched. Human labor adapted itself to these realities because it had no alternative. Nature set the pace. For centuries, this relationship imposed limits on extraction. Forests were certainly harvested, sometimes heavily, but the process remained constrained by practical realities. A workforce could only cut so much timber in a day. Animals could only haul so many logs. Rivers could only transport finite quantities downstream. Distance mattered. Terrain mattered. Human exhaustion mattered. These limitations acted as invisible regulators. No decree was required. No environmental policy existed. The limits emerged naturally from the difficulty of the work itself. A mature oak might require more than a century to reach its full size. Bringing it down demanded patience and coordination. After felling, branches had to be removed. Trunks required cutting and transport. Teams of horses or oxen dragged logs toward collection points. Every stage consumed time. The forest resisted speed. And resistance created balance. German forestry officials understood this relationship well. By the 19th century, they had developed some of the most sophisticated woodland management systems in the world. Detailed records tracked growth rates, harvest cycles, species composition, and long-term yields. Their objective was sustainability. A forest was not merely a collection of trees. It was an asset expected to provide timber for generations. Cutting too aggressively threatened future production. Careful planning therefore became central to forestry management. Yet even the most disciplined systems faced mounting pressure. Industrialization changed expectations. Factories demanded continuous supply. Railway expansion accelerated. Mining operations multiplied. Urban populations grew. What had once been considered adequate production suddenly appeared insufficient. The problem was not that lumbermen lacked skill. The problem was scale. A workforce using traditional methods could not easily satisfy the demands of an industrial nation. Increasing the number of workers helped, but only temporarily. Larger crews introduced logistical complications. Remote forests required housing, transport, food supplies, and infrastructure. Costs rose rapidly. Industrial planners sought a different solution. Rather than multiply labor, they aimed to multiply output. The logic had already transformed manufacturing. Machines enabled a small number of workers to perform tasks once requiring dozens. Production increased. Costs declined. Efficiency improved. Forestry seemed destined to follow the same path. To engineers, the forest increasingly resembled an untapped industrial frontier. The question was no longer whether trees could be harvested. The question was how quickly. Traditional methods began to appear antiquated. Hand tools that had served generations suddenly looked inadequate beside steam engines, locomotives, and mechanized production systems. Investors demanded faster returns. Industrial managers demanded predictable supply chains. Governments demanded resources capable of sustaining national growth. The forest entered a new era. What had once been a workplace shaped by human endurance was about to become a workplace shaped by machines. And machines obeyed different rules. They did not tire. They did not slow with age. They did not negotiate with terrain in the same way men did. Most importantly, they transformed natural limits into engineering challenges. The centuries-old balance between forest growth and forest consumption began to shift. Human effort was no longer the primary constraint. Mechanical power was preparing to take its place. When it arrived, the change would be profound. Forests that had once resisted rapid exploitation would suddenly become vulnerable to a scale of extraction previously unimaginable. The old limits would not disappear overnight. But for the first time in history, engineers possessed the tools to challenge them. and they intended to do exactly that. The solution did not emerge from the forest. It emerged from the factory. By the late 19th century, German engineering had entered an age of extraordinary confidence. Across the empire, machines were solving problems that previous generations had accepted as permanent realities. Steam locomotives conquered distance. Blast furnaces reached unprecedented levels of production. Mechanical presses shaped steel with astonishing precision. Industrial machinery transformed entire sectors of the economy. To many engineers, the forest represented the next frontier. The challenge appeared straightforward. Germany possessed vast woodland resources, sophisticated forestry institutions, and growing industrial demand. The obstacle was extraction. Trees remained rooted in difficult terrain, often far from railways and industrial centers. Harvesting them required labor, time, and expense. Engineers sought to eliminate all three. Their answer was not a single machine but an evolving family of mechanical systems designed to work together. Steam-powered winches, portable saw assemblies, logging railways, cable haulage networks, and heavy extraction equipment began appearing across major forestry operations. Individually, each innovation improved productivity. Combined, they fundamentally altered the relationship between industry and the forest. The philosophy behind these machines was unmistakably German. Every movement was measured. Every delay was analyzed. Every task was examined for efficiency. The objective was not merely to cut trees. The objective was to create a continuous industrial process extending from standing timber to factory gate. Forestry became logistics. A tree was no longer viewed as an isolated organism within an ecosystem. It became the first stage in a supply chain. Engineers mapped forests with increasing precision. Surveyors calculated gradients, transport routes, and extraction zones. Timber stands were categorized according to expected yield. Rail spurs penetrated deeper into woodland regions. Temporary tracks could be laid rapidly and removed once harvesting was complete. The forest itself was reorganized around the needs of machinery. Steam power played a central role. Portable steam engines provided energy in locations previously inaccessible to large industrial equipment. Massive winches hauled timber across distances that would have exhausted teams of animals. Cable systems dragged logs over difficult terrain, bypassing obstacles that once limited productivity. What previously required dozens of workers and animals could now be accomplished by a small crew directing mechanical force. The gains were dramatic. A skilled team using traditional methods might spend an entire day processing a limited section of woodland. Mechanized systems could exceed that output many times over. Investors noticed. Industrial planners noticed. Government officials noticed. Success generated demand for even larger machines. Manufacturers competed to develop stronger cutting systems, more powerful traction mechanisms, and more reliable transport solutions. Engineering journals celebrated innovations that increased productivity. Industrial exhibitions displayed machinery as symbols of national achievement. The machines became expressions of an era's ambitions. Germany's rapid industrial rise fostered a belief that technical expertise could overcome nearly any limitation. Engineers occupied a position of growing prestige. Their calculations shaped railways, factories, bridges, and mines. Increasingly, they also shaped landscapes. The forest giant emerged from this environment. Not necessarily as a single identifiable machine, but as a concept made real through steel, steam, and organization. It represented the concentration of industrial power into a form capable of confronting nature directly. Its purpose was simple: remove obstacles between resources and industry. And in the eyes of planners, forests were resources first. The consequences of this mindset were not immediately apparent. Output increased. Supply chains stabilized. Industrial expansion accelerated. From the perspective of economic statistics, the machines appeared remarkably successful. Timber reached railways faster. Railways delivered materials to factories more efficiently. Factories supported further growth. The system worked, at least in the short term. But hidden within every increase in productivity was a subtle transformation. The old limits that had once restrained extraction were disappearing. Human endurance no longer defined the pace of harvesting. Mechanical capability did. And mechanical capability was advancing rapidly. Each improvement encouraged greater consumption. Each increase in consumption justified larger machines. Each larger machine demanded still greater volumes of timber. The cycle intensified. German engineers had not merely built equipment for cutting trees. They had helped construct a new industrial metabolism, one capable of converting entire forests into economic output with unprecedented speed. The forest giant was born. And its appetite was only beginning to reveal itself. Before it could transform the forest, the machine had to transform energy. That was the true achievement of industrial engineering. For thousands of years, forestry had depended on muscle. Human beings supplied force through labor. Animals multiplied that force through traction. The scale of extraction remained tied to biological limits. A man could only swing an axe for so many hours. A horse could only pull so much weight across difficult terrain. The machine changed the equation. Steam power allowed engineers to separate work from biology. Energy could now be generated by burning fuel and converted into mechanical motion through carefully designed systems of pistons, shafts, gears, and cables. What mattered was no longer endurance. What mattered was power. And power could be increased. The logging machines that emerged across German forestry operations reflected this philosophy. Though designs varied according to region and purpose, they shared a common objective: concentrate enormous force into a controllable mechanism capable of overcoming natural resistance. At the heart of many systems stood the boiler. Massive steel vessels converted water into pressurized steam. Fireboxes consumed coal or wood fuel continuously. Temperatures climbed. Pressure accumulated. Inside the boiler, invisible energy gathered behind layers of riveted steel. The danger was ever present. A boiler failure could release catastrophic force in an instant. Engineers therefore devoted enormous attention to pressure gauges, safety valves, and structural reinforcement. Entire disciplines of mechanical engineering evolved around managing the immense energies trapped within these machines. When functioning properly, the results were extraordinary. Steam entered cylinders where expanding pressure drove pistons back and forth. Connecting rods translated linear movement into rotational force. Flywheels stored momentum. Gear systems redistributed power according to operational requirements. Every component served a purpose. Every movement had been calculated. The machine became a mechanical organism. Power generated in the boiler traveled through shafts, gears, and transmission systems before reaching the equipment responsible for interacting directly with the forest. Cutting assemblies, hauling winches, cable drums, and traction systems all depended upon this carefully coordinated flow of energy. The gears themselves represented masterpieces of industrial manufacturing. Precision machine teeth transferred force between rotating components. Ratios could increase torque or speed depending upon operational requirements. Large gears turned slowly but generated tremendous pulling power. Smaller gears rotated rapidly, enabling cutting mechanisms and auxiliary systems to operate efficiently. The mathematics behind these arrangements was exact. A minor error in alignment could produce destructive vibration. A weak gear tooth could trigger cascading failures. A damaged bearing could disable an entire operation. Reliability therefore became an engineering obsession. The forest was unforgiving. Unlike factory floors, logging environments subjected machinery to mud, moisture, temperature fluctuations, dust, and constant shock loading. Every fallen tree transmitted force through cables and frames. Every uneven surface challenged structural stability. Machines had to survive punishment. German engineers responded with mass. Steel frames grew heavier. Reinforcement increased. Components were oversized to withstand unpredictable conditions. The resulting machines became immense structures capable of enduring forces that would destroy lighter equipment. Weight itself became a tool. Heavy machines remained stable under load. Massive foundations distributed stress. Thick steel plates absorbed impacts. The forest giant relied not only on power but on physical presence. It dominated through sheer scale. The hauling systems were equally impressive. Steel cables stretched across clearings and hillsides. Powered drums reeled enormous loads toward collection points. Logs weighing several tons could be moved with remarkable efficiency. Terrain that once demanded large teams of workers and animals became manageable through mechanical leverage. Distance lost much of its power. The forest, once fragmented by geography, became increasingly accessible. Transport systems extended this transformation further. Temporary railways followed extraction zones into remote regions. Narrow-gauge locomotives hauled timber toward industrial networks. Loading operations were synchronized with harvesting schedules. Delays were minimized. Flow was maximized. The machine did not exist alone. It functioned as part of an integrated industrial system. Cutting, hauling, transport, and processing became interconnected stages of a continuous operation. Forests entered one side of the system. Industrial materials emerged from the other. Efficiency depended upon coordination. Engineers monitored throughput, labor allocation, fuel consumption, and maintenance intervals. Breakdowns threatened productivity. Downtime represented lost output. Every aspect of operation was measured against economic objectives. This pursuit of efficiency drove further innovation. Larger boilers produced greater power. Stronger cables moved heavier loads. Improved metallurgy increased durability. Refined gear systems enhanced reliability. Each advancement expanded capability. Each expansion increased expectations. The machine grew more effective with every generation. Yet hidden within its impressive engineering was a deeper reality. The machine could multiply force. It could accelerate production. It could overcome obstacles that had constrained humanity for centuries. But it could not understand consequences. Steel gears calculated nothing beyond motion. Steam pressure recognized no distinction between sustainable harvesting and overexploitation. Mechanical systems possessed immense capability but no judgment. That responsibility remained human. And as the machine's power expanded, the burden of that responsibility grew heavier than ever before. The machine was doing exactly what it had been designed to do. That was the problem. By the dawn of the 20th century, mechanized forestry had achieved what generations of industrial planners had desired. Timber moved faster. Labor requirements declined. Extraction became increasingly predictable. Supply chains stabilized. The forests that once resisted rapid exploitation had been transformed into manageable industrial assets. From an economic perspective, the system was a triumph. From the perspective of the landscape, it was something else entirely. Efficiency possesses a peculiar logic. When a process becomes cheaper, demand often increases. When production accelerates, consumption expands to match it. Success rarely satisfies industrial systems. It encourages growth. The forest machine entered this cycle immediately. As harvesting costs fell, previously marginal timber stands became profitable. Areas once considered too remote or difficult suddenly attracted investment. New rail spurs pushed deeper into woodland regions. Temporary extraction camps appeared in places untouched by earlier generations of loggers. The frontier moved. Then it moved again. And again. Entire valleys were reorganized around timber production. Hillsides that had remained forested for centuries were surveyed, divided, and scheduled for harvest. Maps increasingly depicted woodlands not as ecosystems but as inventories waiting to be converted into economic output. The pace accelerated relentlessly. Traditional logging crews had been constrained by fatigue, weather, and terrain. Machines weakened those constraints. Work continued longer. Larger volumes were processed. Recovery periods between major harvesting operations shortened. Nature required decades. Industry demanded months. The imbalance widened. Observers began noticing changes that statistics could not fully capture. Forest edges retreated. Wildlife populations shifted. Streams carried greater sediment loads as exposed soil eroded during heavy rains. Areas once sheltered beneath dense canopies experienced new temperature extremes. The machine did not recognize these changes. Its measurements were different. It recorded output, not habitat. Volume, not biodiversity. Productivity, not regeneration. To the machine, a forest represented success when it disappeared according to schedule. This mentality spread beyond individual operations. Forestry managers increasingly adopted industrial metrics. Reports emphasized yield targets, extraction rates, transportation efficiency, and financial performance. The language of production replaced the language of stewardship. Forests became numbers. And numbers encouraged comparison. One district sought higher output than another. Investors rewarded operations that exceeded expectations. Engineers developed methods to reduce delays and eliminate inefficiencies. Every improvement intensified pressure on the landscape. The consequences became visible from railway windows. Travelers crossing parts of Central Europe encountered immense clearings where continuous woodland had once stood. Stumps stretched toward distant horizons. Logging debris littered the ground. Newly constructed tracks cut through exposed terrain. The transformation could occur with astonishing speed. A forest requiring a century to mature might be harvested within a single season. Years of growth vanished in weeks. Centuries vanished in years. Yet few industrial leaders viewed this as evidence of failure. On the contrary, many interpreted it as proof of progress. The machine's ability to reshape landscapes demonstrated national strength. Timber fed mines. Mines supplied industry. Industry produced steel. Steel reinforced the infrastructure of a rapidly modernizing empire. The chain appeared rational. But hidden within that rationality was a dangerous assumption that efficiency itself was inherently beneficial. German foresters had long understood that forests were living systems. Sustainable management depended upon balancing harvest with regeneration. Industrial extraction threatened that balance by compressing time itself. Machines accelerated removal. Nature could not accelerate recovery. The result was a growing gap between what was taken and what could be replaced. In some regions, reforestation programs attempted to address the problem. New seedlings were planted. Scientific forestry expanded. Administrators introduced management plans designed to preserve future yields. Yet even these efforts reflected industrial thinking. Forests increasingly became engineered landscapes. Diversity gave way to uniformity. Mixed woodlands were often replaced with carefully managed stands optimized for production. The objective was not restoration of natural complexity but maintenance of resource supply. Efficiency reshaped the forest even when it sought to save it. The machine's greatest achievement was not simply the number of trees it could remove. It was the transformation of perception. A forest was no longer primarily a living environment. It became a strategic reserve of raw material. Its value was measured according to what could be extracted, transported, processed, and sold. This change proved far more enduring than any individual machine. Steel eventually rusted. Boilers eventually failed. Rail lines were abandoned and rebuilt elsewhere. But the industrial mindset remained. And once a civilization learns to view nature through the lens of production, the appetite for efficiency becomes difficult to restrain. The machine had conquered the limits of labor. Now it was beginning to conquer the limits of the landscape itself. The machine dominated the forest. But it did not work alone. Behind every ton of steel, every spinning gear, every hauled log, stood men whose labor remained essential to the operation. They maintained the machinery, directed the cuts, repaired failures, laid temporary railways, managed cables, monitored steam pressure, and entered danger zones that no machine could navigate independently. The industrial age celebrated engineering. The forest workers lived its consequences. Long before sunrise, camps were already awake. Lanterns flickered between wooden barracks erected near active logging zones. Coal stoves burned through the cold hours. Boots struck packed earth. Coffee boiled in blackened kettles. The smell of smoke mixed with damp timber and machine oil. The day began early because the machine demanded it. Steam boilers required preparation. Fuel had to be loaded. Water levels inspected. Pressure built gradually. Crews performed maintenance checks before the first tree fell. A malfunction discovered after operations began could halt production for hours. Every delay carried a cost. Workers understood this reality intimately. Many came from rural communities where forestry had been practiced for generations. Others arrived from industrial towns seeking wages unavailable in agriculture. Some possessed remarkable technical expertise. Others learned through experience, adapting to a profession evolving faster than tradition could guide it. The work required strength. It also required judgment. A falling tree could kill. A snapped cable could kill. A boiler explosion could kill. A miscommunication between operator and ground crew could kill. The forest machine amplified power, but it also amplified consequences. The danger was constant. Steel hauling cables stretched across clearings under immense tension. Workers often compared them to loaded artillery. A single failure could send metal whipping through the air with enough force to sever limbs or shatter bone. Men learned to read subtle signs of wear, listening for unfamiliar sounds, watching for strands beginning to fray. Experience became a survival tool. Operators occupied a different world. From elevated control positions, they directed forces larger than anything previous generations had encountered in forestry. Through levers, valves, brakes, and mechanical linkages, a single individual could influence the movement of dozens of tons of timber. The responsibility was enormous. Visibility was often poor. Dust clouds reduced sightlines. Steam obscured movement. Weather transformed terrain into mud or ice. Signals could be misunderstood. Decisions had to be made quickly. One mistake might place an entire crew in danger. Yet the machine's pace left little room for hesitation. Productivity targets shaped daily life. Supervisors tracked output carefully. Contracts established delivery schedules. Railways waited for timber shipments. Industrial customers expected consistency. Every part of the system exerted pressure on those working closest to the machine. Fatigue became a silent hazard. Shifts were long. Physical exertion remained intense despite mechanization. Workers spent hours exposed to noise, vibration, weather, and risk. By the end of the day, concentration weakened. Reflexes slowed. Judgments suffered. The machine did not care. It demanded the same attention at sunset as it had at dawn. Injury became an accepted part of the profession. Crushed fingers. Broken limbs. Falling debris. Burns from steam systems. Impact injuries from moving logs. Many incidents never reached official reports. They remained part of camp life, discussed quietly among workers who understood that danger accompanied the wages they earned. Yet despite the hardships, a strong culture developed around the work. Crews depended upon one another completely. Trust mattered. Communication mattered. Knowledge passed from veteran workers to newcomers through demonstration rather than manuals. Men learned where to stand, when to move, and how to recognize subtle warnings that machines themselves could not provide. Survival often depended on collective experience. There was pride as well. Many workers viewed themselves as participants in something larger than individual labor. They were helping build railways, cities, factories, and industries that symbolized national progress. Their work connected remote forests to the economic transformation unfolding across Germany. But pride could not eliminate risk. Every morning, workers entered an environment where enormous mechanical forces interacted with unpredictable natural conditions. They stood between steel and timber, between industrial ambition and physical reality. The machine magnified human capability. It also magnified human vulnerability. And nowhere was that vulnerability more visible than in the moments when power, speed, and error collided. Because sooner or later, they always did. For all its engineering brilliance, the machine possessed a fundamental weakness. It depended upon perfection. Every cable had to hold. Every gear had to mesh correctly. Every pressure gauge had to function. Every worker had to remain alert. Every decision had to be made at exactly the right moment. The larger the machine became, the more fragile this chain of assumptions grew. Industrial reports celebrated output. Newspapers praised technological achievement. Engineers published performance figures demonstrating remarkable gains in productivity. Yet hidden behind those statistics was another reality, one measured not in cubic meters of timber, but in injuries, fatalities, and near disasters. The forest was an unforgiving workplace. Machines multiplied the danger. A tree falling unexpectedly could trigger a cascade of destruction. One collapsing trunk might strike neighboring trees, altering their direction of fall. Branches weighing hundreds of kilograms could descend without warning. Workers standing safely one moment could find themselves directly within a lethal path the next. Mechanization increased speed. Speed reduced reaction time. What once unfolded over minutes could now occur in seconds. Cable failures became infamous among forestry crews. Under heavy loads, steel lines carried enormous tension. Workers respected them with almost superstitious caution. Veterans warned newcomers never to stand within certain zones, never to trust a cable completely, never to assume a load was secure simply because it appeared stable. Experience had taught harsh lessons. When a cable snapped, the stored energy had to go somewhere. The results were catastrophic. Steel recoiled through the air with explosive violence. Equipment shattered. Timber scattered. Men caught in the path rarely escaped unharmed. Survivors described failures that occurred so quickly they barely understood what had happened until silence returned. Steam introduced additional hazards. Boilers required constant supervision. Pressure fluctuations, faulty valves, poor maintenance, or manufacturing defects could transform a productive machine into a weapon. Explosions were rare compared to other accidents, but when they occurred, the consequences were devastating. Fragments of steel became projectiles. Scalding steam engulfed nearby workers. Entire crews could be injured within moments. Even routine operation carried risks. Moving machinery created countless pinch points, crushing zones, and entanglement hazards. Clothing caught in rotating components. Hands slipped during maintenance. Workers climbed onto equipment to perform adjustments under difficult conditions. Fatigue magnified every danger. And fatigue was unavoidable. The machine rewarded speed. Industrial schedules rewarded output. Economic pressure rewarded uninterrupted operation. As a result, many accidents emerged not from a single mistake but from accumulated exhaustion. A worker misjudged distance. An operator failed to notice a signal. A maintenance inspection was rushed. Small errors combined into major incidents. The pattern repeated itself across industrial history. The machine itself rarely intended harm. Its danger emerged from scale. A handsaw could injure. A steam-powered forestry system could kill multiple workers through a single failure. The multiplication of power inevitably multiplied consequences. Investigations often reached similar conclusions. Human error. Procedural oversight. Mechanical defect. Environmental conditions. All were technically correct. Yet these explanations sometimes obscured a deeper truth. The machine demanded conditions that humans struggled to maintain indefinitely. Perfect concentration. Perfect communication. Perfect maintenance. Perfect timing. Reality rarely supplied perfection. Workers knew this better than anyone. They carried scars proving it. They attended funerals proving it. They learned that industrial power always came with a price, even when official reports reduced tragedy to statistics and technical language. The machine could flatten forests. It could feed furnaces. It could accelerate the rise of an industrial empire. But every increase in capability widened the gap between what the machine could do and what human beings could safely control. And in that widening gap, accidents became inevitable. Not because the workers lacked skill. Not because engineers lacked intelligence. But because immense power, once unleashed, always creates risks proportional to its strength. The forest remembered those risks. The workers remembered them too. The trees did not disappear for their own sake. They disappeared because something larger was waiting for them. Far beyond the forests, beyond the logging camps and temporary rail spurs, stood the true destination of this vast extraction system. Blast furnaces glowed through the night. Steel mills thundered with continuous production. Coal mines descended deep beneath the earth. Railway networks expanded across the continent like iron arteries. The machine in the forest was only the beginning. Every log it harvested entered a chain of industrial transformation that connected remote woodlands to the heart of German power. Railways consumed enormous quantities of timber. Wooden sleepers supported thousands of kilometers of track, binding together cities, ports, mines, and factories. As the network expanded, so too did the demand for replacement materials. A modern industrial nation required constant maintenance, and maintenance required wood. The mines demanded even more. Deep underground, millions of timber supports held back the immense weight of the earth. Without them, tunnels collapsed. Production halted. Entire operations became impossible. Every meter driven deeper into coal-bearing rock increased the appetite for forest products above. Then came the furnaces. Though coal increasingly dominated industrial fuel systems, timber and wood-derived products remained critical components throughout many industrial processes. Charcoal production, construction materials, transport infrastructure, and auxiliary industries all depended upon a reliable supply of harvested wood. The result was an extraordinary flow of resources. Forests became mines above ground. Trees became structural components, transport systems, industrial inputs, and strategic assets. Their value was measured not by their existence, but by their conversion into something else. This conversion helped fuel Germany's rise into one of the world's foremost industrial powers. Steel production expanded. Railway mileage increased. Cities grew. Factories multiplied. Economic output surged. The empire of iron consumed forests, and the machine ensured that consumption could continue at unprecedented speed. Yet the relationship was never equal. Iron endured for decades. The forest required generations to return. Industrial growth measured success in annual figures. Nature measured recovery in lifetimes. And as Germany's industrial strength rose higher, the forests paid the price in silence, one harvested valley, one cleared hillside, one fallen tree at a time. When the machines finally fell silent, the consequences remained. The steam engines cooled. The cables rusted. The temporary railways disappeared beneath grass and soil. Workshops closed. Logging camps were abandoned. Many of the machines that once seemed unstoppable were dismantled, scrapped, or forgotten. But the landscapes they transformed could not be dismantled so easily. Across large sections of Central Europe, the marks of industrial forestry endured for generations. Forests returned in some places, but they often returned differently. Ancient mixed woodlands that had evolved over centuries were replaced by carefully managed plantations designed for predictable yields. Diversity gave way to uniformity. Efficiency remained embedded in the landscape long after the machines themselves had vanished. The change was not merely environmental. It was cultural. German forestry became one of the most scientifically managed systems in the world. Foresters, engineers, and policymakers increasingly understood that industrial capability without restraint could threaten the very resources upon which industry depended. New management strategies emerged. Harvest cycles were refined. Reforestation programs expanded. Long-term planning became essential rather than optional. The lessons had been expensive. The machine had proven that humanity possessed the power to transform nature on an unprecedented scale. It had also demonstrated that power alone was not wisdom. The forests fed railways that connected cities. They supplied mines that powered industry. They helped create steel that built bridges, factories, ships, and entire economies. In a very real sense, those fallen trees became part of modern Germany itself. Their fibers, fuel, and structure were woven into the foundations of industrial civilization. Yet every achievement carried a shadow. Behind every production record stood a landscape altered. Behind every engineering triumph stood workers exposed to danger. Behind every symbol of progress stood a question that remains relevant long after the age of steam. How much should be taken in the pursuit of growth? The forest machine never answered that question. Machines rarely answer questions. They execute instructions. They amplify intentions. They transform human ambition into physical reality. And that is why the true legacy of the forest giant is not found in steel, timber, or industrial statistics. It is found in the realization that engineering power and human judgment must advance together. Because when the ability to reshape the world grows faster than the wisdom to guide it, even the greatest achievements can leave scars that endure for generations. The forests remember. History remembers. And the empire of iron they helped build stands as both monument and warning.